Hello everybody, welcome back today. And today we're going to be talking about tortoises and hares. And you might be thinking, what are we actually talking about? Like, usually you make like CS videos. What is this about? Well, obviously you must have all heard that, the tortoise reached the finish line first before the hare, but this is not about the race. It's about lead code. So this is an actual algorithm that is used in a lot of linked list questions to detect if there's a cycle in a linked list or not. If you don't know what that means, don't worry about it. This is what we're going to talk about. So let's get to it. All right, so we're going to talk about the tortoise and hare algorithm, right? Here we have our tortoise and hare. As I said, it's a linked list algorithm, right? So we have some linked list right here. And like I said, we want to detect if a linked list has a cycle. So what do I mean by that? So a linked list, we know, is has the current node value and it's connected to a next, right? It has a link to the next. However, sometimes in between our linked list, we can have, for example, like at the end, this end node, it could have a link to something before, right? And if it does, we consider that to be a cycle in the linked list, which means that it goes back to a previous node that was already, traversed through. So when you get to 5, when you go to the next is actually 3, which is back here. So we want to detect if we have a cycle. Now, how could we do that? Well, one thing we could think about is like if we go through all of them and then come back, right? We go through all the nodes and then we come back and we see every time, is this something we visited before? If so, then we know we have a cycle. So that could be implemented using something like a set, right? Where you push every node into the set and then you check every time you traverse through the thing, have I seen this before? If I have, then yeah, then I have a cycle. However, this is not really the best way because one, this is O of n memory, and we don't need that. We can do this in O of 1 memory, and so the best way to think about this is the sort of tortoise and hare algorithm. So how is this done? So a very key part of a linked list are that you can actually do a slow and a fast pointer. So we can have slow pointers and then we can have fast pointers. What this means is this moves one node at a time, the slow pointer, and the fast one actually moves 2 nodes at a time. So this is sort of like a mathematical proof thing, but if you ever actually done questions like where they ask you like there's one runner that's going in a circular path and there's another runner that's going twice as fast, will they ever meet? Well, we know they meet because it's a circular path, right? So a cycle is something similar. We know that there's some point where it's going to cycle around to a previous node. So what we can have is we can have a slow pointer and a fast pointer. So what that means is we have both our slow and fast starting at the initial node, but the slow one moves 1 at a time, right? And then the fast one moves at 2 at a time. So it goes here. So in fact, let me use different colors to distinguish. So this is our slow pointer and this is our fast pointer. So every iteration, right, a slow pointer is moving 1 at a time. However, our fast pointer is moving 2 at a time. So now our fast pointer is here. Then my slow pointer will be here, and then my fast pointer will be here. And then my slow pointer is here. My fast pointer, since it's a cycle, it comes back. So my fast pointer is actually here again, right? So it's again here because it comes back here. My slow pointer is going to move over one more. So I'm here, and then my fast pointer, that one that's right here, will go here again. So now we see that the slow and the fast pointer are at the same location, right? They're at the same spot, right? So since they have the same location, that means we know we have a cycle. If they did not meet at the same location at a certain point, and then we see that our fast is is null, or like the pass dot next is null, right? Because we're moving 2 at a time. If we see that to be the case, then that means there is no cycle. But if the slow and fast meet, as we saw here, slow and fast meet, then there is a cycle, right? But key differentiation right here. The key note is the point at which they meet is not necessarily where the cycle is, right? Is now here in this case it was where the cycle, the next variable was the cycle, but that doesn't necessarily happen. So don't think that the point where they meet is not the cycle point. Okay, so that's a key thing to keep in mind. It's not necessarily always going to work out that way mathematically. However, this is sort of the basis of how you do the tortoise and hare algorithm. So now let's go over to LeetCode and code this out. Alright, so this is the LeetCode question here, LeetCode 141, LinkedList Cycle, and it gives you a head pointer to the linked list, and wants you to determine if the linked list has a cycle. So we're going to return a Boolean, as you can see here. So again, well, we talked about the tortoise and hare algorithm, correct? So here they gave us a few examples, right? Here the -4 node has a cycle to 2, and they tell you where the position is, right? This one they don't actually give us in the method, but they just tell us that just so we can understand the question. So they do that, and if there's no cycle, we want to return false, right? So let's get started with our explanation here, or our code here from our explanation. So we have a list node, and we want a slow pointer, as I said. And at the start, like I said, they're both going to point to the same location, which is our head pointer, correct? So we have these two nodes here pointing to this location. What we'll do is, like I said, we'll keep iterating until our fast gets to null, right? There's a point, if there's no cycle, our fast will get to null first, and in that case, we can't ever cycle back, correct? Because if our fast is null, there's no way that it's ever going to go back. So we need to make sure our fast is not equal to null, and we need to make sure our fast.next is not null, because since the fast is moving one node at a time, we want to make sure that the next is not null, because then otherwise there's no way it's going to cycle back either. So these are the two cases we need to know. And in here, we're going to check if they ever hit, if same and fast are same location, then we know it's true, right? If not, this while loop will end at some point, and we know it'll be false. So this is our end case, kind of. We know in this case there is no cycle, right? So this one we're sure of here. Now we need to do the logic here. So we need to make sure our slow and fast move this. We move the slow and fast. So we move slow to next, right? So slow is equal to slow.next. So we want to move it one over. Same thing here, fast, but fast moves next to next. So meaning it moves 2 over every time. So that way there was actually one going slow and the other one's actually going fast. Next, at the end we just check if slow is equal to fast, right? And they give us the class here. I don't think they really they don't actually overload the equals operator, but that doesn't really matter here because the node references aren't really changing, so we don't have to worry about that. But yeah, if slow is equal to fast ever, we automatically know that there is a cycle, and we just return true. Again, remember, they don't ask us where the cycle is or where it's occurring. We just know, we need to know if there is a cycle. And this is a O in 1 memory time, right? Because that's what the follow-up is. Can you do it in O of 1 memory? We could, however, again, like I mentioned, we could do this with a stack and hold these list nodes every time as we visit them. If we visited them, so it would be the same thing. We'd have one pointer and we'd keep moving and we'd add it to the stack. So we'd see if I've seen this node before, then I know it's a cycle. That means I can just return true and just not do anything. Otherwise, I add to my stack. I keep adding. At the end, if I reach till the end of the linked list and I still haven't returned true, then I know I returned false. So it's the same logic, but this one takes O of n memory, right? Whereas we can do this in O of 1 memory with the tortoise and hare algorithm. So let's just run this just to make sure we don't have any compiler errors that could pop up. And we pass these base cases that they have, and then we'll submit. And delete code will take its sweet time, and there we go, beats 100%. So it's a very valid solution. So yeah, again, I hope you enjoyed the algorithm. It's not something that you would expect. Tortoise and hare, it's like, why is this here? This is something like we learned in elementary school, but the concept is so important in this lead code style question, and the concept of slow and fast pointers are super important in lead code questions, especially for linked lists, especially in algorithm questions that they ask in interviews and stuff. So it's a very important concept to know. So I hope you enjoyed this video. Let me know in the comment section below if you want to see some other videos like this or some other niche algorithms that you're interested in. But otherwise, make sure to like the video, subscribe to the channel, make sure to share it with your friends and family. But otherwise, I hope to see you soon.